Have you ever wondered what the universe is made of? It's a question that has fascinated humans for centuries. We look up at the night sky and see countless stars, but what are those stars made of? What are we made of? The answer, it turns out, is incredibly small. So small, in fact, that we need powerful machines just to glimpse them. These tiny particles are the elementary particles, the fundamental building blocks of everything we see and interact with. They are the very essence of the cosmos. Understanding these elementary particles is like learning the alphabet of the universe. Just like letters combine to form words, these particles come together to create everything from the air we breathe to the distant galaxies. It's a fascinating world governed by the laws of quantum mechanics, where things aren't always as they seem. In this journey, we'll delve into the heart of matter itself. We'll explore the strange and wonderful world of quantum physics and uncover the secrets of these elementary particles. So, buckle up and get ready for an adventure into the smallest scales imaginable. Don't miss to subscribe to our channel, like the video, and hit the bell icon to stay updated with our latest content. To understand elementary particles, we need to venture into the quantum realm. This is a domain where the rules of classical physics no longer apply, and the behavior of particles is governed by the strange and fascinating laws of quantum mechanics. This is a world very different from our everyday experiences. While we are accustomed to the predictable behavior of macroscopic objects, the quantum realm operates on an entirely different set of principles. Here, things aren't so clear-cut. Particles can exist in multiple states at once, and their properties are not defined until they are observed. Particles can act like waves, and certainty gives way to probability. This dual nature is one of the most intriguing aspects of quantum mechanics, challenging our understanding of reality. Imagine a world where you can never know both the exact position and speed of a particle. This is not just a limitation of our measurement tools, but a fundamental property of nature itself. This is the essence of Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics. It tells us that the more precisely we know one property, the less precisely we can know another. It's a world where particles can pop in and out of existence, borrowing energy from the vacuum of space itself. These fluctuations are a testament to the dynamic and ever-changing nature of the quantum realm. In this strange and wonderful realm, we encounter two fundamental types of particles, fermions and bosons. Fermions make up the matter we see around us, while bosons are responsible for mediating the forces that act upon this matter. These particles are the actors on the quantum stage, playing out their roles according to the laws of physics. Their interactions and behaviors are dictated by the principles of quantum mechanics, leading to a rich tapestry of phenomena. Fermions are the building blocks of matter, while bosons are the messengers of the fundamental forces. Together they create the complex structures and interactions that make up our universe. Together, fermions and bosons make up the standard model of particle physics, our best attempt to create a comprehensive theory of the subatomic world. This model has been developed over decades of research and experimentation, and it continues to evolve as we make new discoveries. It's a model that has been incredibly successful in explaining a wide range of phenomena, from the behavior of atoms to the interactions of particles in giant colliders. These colliders, such as the Large Hadron Collider, allow us to probe the deepest mysteries of the quantum realm, revealing the fundamental building blocks of the universe. One of the most fascinating aspects of quantum mechanics is the phenomenon of quantum entanglement. This occurs when particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. The principles of quantum mechanics are not just theoretical, they have practical applications as well. Quantum computing, for example, leverages the unique properties of quantum bits, or qubits, to perform calculations that would be impossible for classical computers. As we continue to explore the quantum realm, we are uncovering new possibilities for technology and understanding. From quantum teleportation to advanced materials, the potential applications of quantum mechanics are vast and exciting. The journey into the quantum realm is far from over. With each new discovery, we gain a deeper understanding of the universe and our place within it. The future of quantum mechanics holds endless possibilities, and we are only just beginning to scratch the surface. Let's start our exploration with fermions, the particles that make up everything we can see and touch. These particles are the building blocks of atoms, the basic units of matter. Without fermions, there would be no stars, no planets, and no us. Fermions are divided into two main groups, quarks and leptons. Quarks are the particles that make up protons and neutrons, the particles found in the nucleus of an atom. Leptons, on the other hand, include electrons, the negatively charged particles that orbit the nucleus. One of the defining characteristics of fermions is that they obey the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state simultaneously. Think of it like a game of musical chairs, where each chair is a state. Only one fermion can occupy a chair at a time. This simple principle has profound implications for the structure of matter. It's what prevents atoms from collapsing in on themselves and gives rise to the incredible diversity of chemical elements we observe in the universe. Don't forget to subscribe to our channel and hit the bell icon to stay updated with our videos. Quarks, the tiny building blocks of matter. Let's zoom in even further and explore the fascinating world of quarks, the fundamental constituents of matter that are even smaller than protons and neutrons. These particles are incredibly small, even by subatomic standards. To give you an idea, if a proton were the size of a football field, a quark would be smaller than a grain of sand. In fact, they're so small that we've never actually seen a quark directly. Instead, we rely on indirect evidence from high-energy particle collisions to study them. Instead, we infer their existence from the way they interact with other particles. These interactions leave behind tracks and patterns that scientists can analyze to understand quarks better. Quarks come in 6 different flavors: up, down, sharp, strange, top and bottom. Each of these flavors has unique properties that contribute to the behavior of the particles they form. These whimsical names have no relation to their actual properties, but they do make it a little easier to keep track of them. The names were chosen to be memorable and to distinguish between the different types. Each quark also carries a fractional electric charge, a property that distinguishes them from other particles. This fractional charge is a key feature in the formation of larger particles. For example, the up quark has a charge of plus 2/3, which means that it contributes a positive charge to the particle's while the down quark has a charge of minus 1/3. This negative charge balances out the positive charges of particles like neutrons. It's these fractional charges that give protons and neutrons their overall electric charge. For instance, a proton is made up of 2 up quarks and 1 down quark, giving it a net positive charge. Quarks are always bound together by the strong force, one of the 4 fundamental forces of nature. This force is incredibly powerful, much stronger than gravity or electromagnetism. This force is so strong that it's impossible to isolate a single quark. No matter how much energy you put in, quarks will always pair up or form groups. They always exist in groups of 2 or 3, forming particles like protons and neutrons. These groupings are essential for the stability of matter as we know it, making quarks the true building blocks of the universe. Leptons, the other half of matter. In the vast and intricate world of particle physics, leptons hold a special place. They're fundamental particles that, along with quarks, make up the building blocks of matter. Now let's turn our attention to leptons, the other group of fermions. Fermions are particles that follow the Pauli exclusion principle, meaning no two fermions can occupy the same quantum state simultaneously. This principle is crucial in defining the structure of matter. Unlike quarks, leptons are not subject to the strong force. The strong force is what holds quarks together within protons and neutrons, but leptons are free from this interaction. They interact primarily through the electromagnetic force and the weak force. The electromagnetic force is responsible for the interactions between charged particles, while the weak force is involved in processes like beta decay. The most familiar lepton is the electron, a fundamental particle that plays a crucial role in chemistry and electricity. Electrons are found in the electron cloud surrounding the nucleus of an atom. Electrons are responsible for the chemical bonds that hold atoms together and the flow of electrical current. Without electrons, the very fabric of matter as we know it would not exist. In addition to electrons, there are 2 other charged leptons, the muon and the tau. These particles are similar to electrons but are much heavier. These particles are much heavier than electrons and are highly unstable, decaying rapidly into other particles. The muon, for instance, decays into an electron and 2 types of neutrinos. Each charged lepton also has a corresponding neutral partner called a neutrino. Neutrinos are fascinating because they have very little mass and no electric charge. Neutrinos are incredibly elusive particles that interact very weakly with matter. This makes them extremely difficult to detect, requiring sophisticated equipment and large detectors. Billions of neutrinos from the sun pass through your body every second without you even noticing. These neutrinos are produced in the core of the sun during nuclear fusion reactions. Leptons, like quarks, come in 3 generations. Each generation is associated with a different set of particles, each heavier and more unstable than the last. Each generation is heavier and more unstable than the previous one. The first generation is the lightest and most stable, while the third generation is the heaviest and least stable. The first generation consists of the electron and the electron neutrino, which are the most stable and common in the universe. The second generation includes the muon and the muon neutrino, which are less stable and heavier than their first generation counterparts. And the third generation comprises the tau and the tau neutrino. These particles are the heaviest and most unstable, existing only for a fleeting moment before decaying into lighter particles. Leptons play a crucial role in the universe, from the smallest scales in particle interactions to the largest scales in cosmic phenomena. Understanding leptons helps us unlock the mysteries of the universe and the fundamental forces that govern it. Scientists study leptons using particle accelerators and detectors, conducting experiments that reveal their properties and interactions. These experiments are essential for advancing our knowledge of particle physics. Theoretical models and equations also play a significant role in our understanding of leptons. These models help predict the behavior of leptons and their interactions with other particles. Leptons are an integral part of the Standard Model of particle physics, which is the current best theory describing the fundamental particles and forces in the universe. The study of leptons continues to be a vibrant and exciting field of research. As we look to the future, the study of leptons promises to yield even more discoveries, deepening our understanding of the universe and the fundamental nature of matter. Please subscribe to our channel, like the video, and hit the bell icon to stay updated with our latest content.